go over hypothesis tests for paired data. This example, we have cholesterol levels of patients before and after a 6-week vegetarian diet, and we're going to assume that cholesterol level is normally distributed. For Abe, the cholesterol before the diet was 260, after 220, difference is 40. For Barb, 320 before the diet, 200 after, difference is 320 minus 200 is 120. Cindy, 240 before the diet, 260 after the diet, 240 minus 260 is negative 20. So it's a negative number if the cholesterol level goes up. It's a positive number if it goes down. For paired data, we need to treat that differently than data from independent samples. These samples are not independent because it's the same person, different readings from the same person before and after. So basically we're going to treat this as a single set of data. We're going to focus on this last column here, which is the difference, and test whether the difference is different from 0. And so we're going to need the mean of the mean difference as 34.5, and the standard deviation of the difference is 29.1 something. We're going to need that information. So we want to test with 95% confidence. H0, the mean difference is equal to 0, diet is not effective, versus HA, the mean difference is, or mu d is greater than 0, diet is effective. So this is a one-sided test, so we want to get the critical value from the t-table. Our sample size is 20, 21 minus 1 is 19, so because it's a one-sided test, we'll use alpha rather than alpha over 2. So alpha is 0.05. Look in row 19, column 0.05 of the t-table, and this is it's in the appendix. I switched textbooks, so it's not that page number referred to a different text. To get the upper critical value of 1.729. And then we want to compute the test statistic that the mean difference, which is 34.5, times square root of n, which is square root of 20, divided by the standard deviation of the difference, which is 29 point something. And so the test statistic comes out to be 5.301. Our test statistic is more than the critical value of 1.729. So we reject H0 with 95% confidence and conclude that the diet was effective in lowering cholesterol levels. In fact, because our test statistic is more than any number in row 19 of the t-table, the p-value is less than 0.005, and actually provides strong evidence that the diet is effective. And to use these formulas, some texts require that the sample size be at least 30 or the variable is normal, but ours does not require that. Okay, we can also you can also have paired data for proportions. A sample of 1,000 patients was divided into 500 pairs, matched by age and clinical condition. One person in each pair was given treatment A, one person in each pair was given treatment B, and the results are given in the table. So this is a fairly standard practice here of matching patients by age and clinical condition, and then giving seeing what the results of different treatments are. Okay, so in 400 pairs, both patients were cured, and this top row is the A cured row. First column is the B cured column. For 20 patients, A was cured, but B was not. Total of 420 pairs, and total of 420 pairs, A was cured. 30 pairs, B was cured, but A was not. 50 pairs, neither was cured. 30 plus 50 is 80. There's 80 pairs where A was not cured. the B totals are 40 for 30 cured, 70 not. But we want to sort of focus on the pairs where the outcomes were different. So we're going to focus on the 20 pairs where A was cured and B was not, and 30 pairs where B was cured and A was not. So we want, let's set our confidence level to be 95%. So 1 minus alpha is 0.95, alpha is 0.05. We want to test H naught, response is independent of treatment, versus HA, response depends on treatment. And again, we're focusing on the pairs where the outcome was different for the two treatments. So the NA is 20 pairs where treatment A was better, and B is the 30 pairs where treatment B was better. We want to check that NA plus NB has to be at least 20, and it is. 20 plus 30 is 50, which is more than 20. If not, binomial probabilities would need to be used. And then we want to compute the test statistic, absolute value of NA minus NB, and then subtract 1 and then square it, divide by NA plus NB. So 20 minus 30 is negative 10, absolute value of negative 10 is 10, 10 minus 1 is 9, 9 squared is 81, 81 divided by 50 is 1.62. So then we want to compare it to the number from the table. It's a one-sided test, so we're going to use alpha rather than alpha over 2. Look in row 1, column 0.05 of the chi-square table to get the critical value of 3.841. Our test statistic of 1.62 is less than the critical value, so we fail to reject H naught. Sample does not provide enough evidence to say that response depends on treatment. And that concludes this presentation.